Hello and welcome to the second video for C5 and C7 revision for GCSE chemistry. In this video we'll be looking at making salts, the pH scale and strong and weak acids. To start off, I would like you to answer these three questions based on the previous video. Please pause the video now to answer the questions. The answers are on screen now. We're now going to have a look at making salts from metals. So if we take a metal and we want to make a salt, we need to add an acid to it. Whenever we take a metal and an acid, we will make a salt plus hydrogen. Now, this will only happen if the metal is more reactive than hydrogen. So I have a trough here filled with a dilute acid. If I put some copper or some silver in the trough, I would get no reaction. That's because copper and silver are both less reactive than hydrogen. Now this piece of metal here represents a metal that is more reactive than hydrogen. It could be magnesium or zinc. And when I put a piece of magnesium or zinc into an acid, I will notice that I will start getting some bubbles of gas being given off. And we can call this fizzing or effervescence. If you ever see fizzing or effervescence when a metal is added to an acid, we are getting a gas given off. And that gas is hydrogen. We have hydrogen gas being given off, and we will have a salt left in the solution. Now, the type of salt that we get depends on the type of acid. So if we look first at hydrochloric acid, which is HCl, we need to look at the negative ion, the anion, that is left after the hydrogen has been displaced. In this case, we have a chloride ion, which is Cl-. Our salts will all be chloride salts. For nitric acid, our formula for nitric acid is HNO3. Again, we need to look at our negative ion in this compound, and we will get our NO3-. So all nitric acids will form nitrate salts. Our sulfuric acid, we have our formula H2SO4. Again, we need to look for the negative ion, which is our SO4. Our charge on an SO4 ion is 2-. All of our sulfuric acids will form sulfate salts. And we can use this information to see what salt we will get, and also use the charge on our ions for our salts to work out the formula for those salts, as well as using that to help us write our balanced symbol equations. We're now going to look at making salts from insoluble bases. Again, we need to make sure we know a few of these words. So insoluble is something that does not dissolve. And a base is something that will neutralize an acid. We have a general equation for this, and we can work it out. If we take a base and want to make a salt, we need to add something to that base so that we can get a salt. It won't just turn into a salt by itself. We need to have an acid. And that acid will provide that negative ion for the salt. Because we've got an acid and a base reacting together, we will also form water. Now, a nice one that we've done in school before is making copper sulfate from copper oxide. So to do that, we have a beaker full of dilute acid, and that acid is sulfuric acid. To that sulfuric acid, we will add copper oxide. And it is copper 2 oxide, which is a black powder. And we will add it to it, and we will add it to it in excess. So there is more than enough. We then get this black powder at the bottom. If we stir it, and we make sure we do it in a warm environment, we will start seeing that the solution will change colour and turn blue. That blue colour, or the now aqueous solution, is copper 2 sulfate. And it is aqueous. It is a salt. It has now dissolved in the water. The oxide has combined with the hydrogen to form water. So we now just have H2O on there. At this point, we might want to collect the copper sulfate, in which case we would need to use separating techniques such as filtration and evaporation to get the copper sulfate crystals. But if we want to look at our equation for this, we would have, looking at our general equation, we've got sulfuric acid plus copper oxide, or copper 2 oxide, will make copper sulfate and water. That is our word equation. We can also write our balanced symbol equation. So we have H2SO4 plus CuO, it's copper 2, so it has a charge of 2 plus, will make copper sulfate, which is CuSO4 plus H2O. And we can look at this and see that it is already balanced. We have the same number on each side. We can also add in state symbols if we wanted to as well. But our rule for making a salt from an insoluble base is an acid plus a base will make a salt plus a water. We're now going to have a look at making salts from alkalis. Now, an alkali is very similar to a base, but this time it is a soluble base. So it will neutralize an acid, but it can dissolve in water. Now, our soluble bases will all have an OH ion, and most of them will be hydroxides. And that OH ion is what makes them an alkali. Again, we have a general equation. We have an acid plus an alkali will make a salt plus water. Now, this is an example, just like the last one, of a neutralization reaction. An acid and an alkali, or an acid and a base, mixed together, we have a neutralization reaction potentially occurring, especially if we get to water at the end. To do that, we need to make sure we add the correct amount of the alkali to the acid, otherwise we will make it either not neutral, it'll still be acidic, or it will go to alkaline. So we need to add the correct amount. Add the correct volume. To do this, we use something called titration. And we have a setup where we would have a conical flask which has acid inside it. We use hydrogen chloride. We then have a clamp stand, and we would have what we call a burette. Now, a burette is a long device that has values labelled on it. This is a burette. And we can measure very, very accurately how much is being added. Inside the burette, or on the side of the burette, we have values, so we can measure the amount given. However, these values will go almost what we think is the wrong way. We'll start from 0 and go down to 100, and this shows us how much has been added. We need to make sure that we start at the top, and whenever reading from a burette, we read from the tip of the meniscus. If we look at one here, so we've got our values there, so we'll go from 10, 10.1, 2, 3, 4, 5, 6, 7, 8, 9, to 11. So each one of these graticules is 0.1 milliliters. The meniscus is the bottom part here, and that's where we need to read from. So if we wanted to read how much had been added on here, we would read to this point here, and we would make sure we go from 10 and count down. So it's 10, 10.1, 10.2, 10.3 to 10.4. That is our value there. That is in milliliters or centimeters cubed, or any measure of volume. Finally, we're going to have a look at making salts from carbonates. Now, a carbonate has a CO3 ion attached to it. Again, we have our general rule. And we're going to focus on the metal carbonates. And again, we're going to add an acid to it. If we have an acid plus a metal carbonate, we're going to make some slightly different things. And with this, we're going to make a salt again. We're always making salts with these. We're also going to make water, and we're going to produce carbon dioxide. This is our general equation. An acid plus a metal carbonate will make a salt, water, and carbon dioxide. So we'll have a look again at a word equation for one. So we have here sulfuric acid plus magnesium carbonate. Because we've got sulfuric acid, we're going to make a sulfate salt. We need that magnesium ion as well. So we'll have magnesium sulfate. Plus we will make water and carbon dioxide. That carbon dioxide is given off as a gas. We can then write our balanced symbol equation for it as well. So sulfuric acid is H2SO4. Our magnesium carbonate is MgCO3. And that should tell you what the charge is on the carbonate ion. We'll make magnesium sulfate, which is MgSO4, plus water, which is H2O, plus carbon dioxide, which is CO2. We can then check that we've got the right number of atoms on each side, check that it is balanced. In this case it is. We have the same number of atoms on each side, so we don't need to do anything further. If you aren't sure about balancing equations, do have a look at the balancing equation videos on the CHSG channel. There are now 5 questions for you to answer. Please pause the video to answer these questions. The answers are on screen now. So we're going to look at neutralisation and the pH scale. The pH scale is a scale that goes from 0 to 14. So in the middle we have the number 7. The pH of below 7, so from 0 up to 7, we have things that are acidic. Now, acids will all release H+ ions. So they all have hydrogen ions. The more hydrogen ions there are in a solution, the more acidic it is. The other side of the pH scale, so going from 7 up to 14, we have our alkalines. Now our alkalines in a solution will release OH- ions. That's what turns something alkaline. We can tell the pH of a solution by using universal indicator. At the very bottom we have a red colour. So if universal indicator is added and we get a red solution, it has a pH, a very low pH. We add it and we get a purple colour, we have a very high pH. If we add it and we get green, we have a neutral solution. This is neither acidic nor alkaline. It has equal numbers of H+ and OH- ions. These ions will combine together to make H2O, which is water. Now, the pH scale and with universal indicator follows the same pattern as a rainbow. So we have red, orange, up to yellow, and then green for neutral. Past green we get to a light blue, a bit of a darker blue, very dark blue, and then that lovely purple colour. So by looking at the colours that have been added, or the colour the solution turns when universal indicator is added, lets us know the pH of the solution. Now when we take an acid and we react it with an alkali, remember it is a soluble base, contains those hydroxide ions. A base itself is not soluble. Alkali is a special type of base. It will make water. We will also get a salt as well. The reason we get water is because the H+ ions from the acid and the OH- ions from the alkaline will combine together to make water. The other parts from the acid and the alkali, so our other ions, will make the salt. You now have 4 questions to answer. Please answer these. Please pause the video and answer these questions. You should now only be watching if you've answered all 4 questions. The answers are on screen now. Finally, we're going to look at strong and weak acid. Now, we already know that when an acid is in a solution, the H+ ions are what cause it to be acidic. We can have different strengths acids. So I've got a beaker here filled with water, and I'm going to add hydrogen chloride gas into it, and it's going to dissolve. When it dissolves, it splits up into H plus ions and Cl minus ions. And they are all free to move around. Now the important thing here is that all of the H plus, or all of the hydrogen chloride, is ionized. So in a strong acid, it ionizes completely in the solution. All of the H plus and Cl minus ions split up and it ionizes completely in the solution. We have no free or no HCl's left together. They've all split apart. If we have a look at a weaker acid, so if we look at ethanoic acid or vinegar, which is CH3COOH, it is this H here that will ionize. When we put it into the solution, we have some of the some of it will ionize, other parts will stay together. That is because it is a reversible reaction this time. We have CH3COOH, reversible reaction sign. It will reach a state of equilibrium. Now, in a weak acid, only some of only when you get partial ionization. And we only get partial ionization. And this means we have less H plus ions around than we do in the other one, with our hydrogen chloride one. So our strong acids will include things like our hydrogen chloride, sulfuric acid, nitric acid. Our weak acids will include ethanoic acid, citric acid, and carbonic acid. We're now going to have a look at how the concentration of hydrogen ions relates to the pH. So we're going to look at the concentration of H plus ions in moles per decimeter cubed. Now when the concentration of H plus ions is 0.1 moles per decimeter cubed, we have a pH value of 1. When the concentration of H plus ions is 0.01, we have a pH of 2. When the concentration is 0.001 moles per decimeter cubed, we have a pH of 3. The concentration is 0.0001 moles per decimeter cubed. We have a pH of 4. We can see here that when we go down by 1 on the pH, we increase by a factor of 10. So we have a logarithmic scale. Again, if we look at, if we had a pH of 6 and we wanted to compare it to a pH of 3, you might be tempted to say that a pH of 3 is twice as strong as pH of 6. It's not twice as strong, so though we've halved it, we need to think about how we're going. So we'll write 6, 5, 4, 3. A pH of 5 is 10 times stronger. A pH of 4 would be 100 times stronger. A pH of 3 would be 1,000 times stronger than a pH of 6, because we follow this logarithmic scale, just like how they do with measuring earthquakes. There are now 3 questions on screen for you to answer. Please pause the video to answer these questions. You should now have answered all 3 questions and are ready to mark your answers. Please pause the video to mark your answers. Thank you very much for watching the video. Have a good day. Bye bye.